Hello and welcome to this lecture on measures of variability, also called measures of spread or measures of variation. After this lecture, students should be able to explain the importance of measuring variability, calculate and interpret the index of qualitative variation, range, interquartile range, the variance, and the standard deviation, and identify the strengths and weaknesses of each of these measures as well as when to use them. Measures of variability, or variation, or spread, are numbers that describe the diversity or variability in a distribution. While measures of center provide us a window into the typical case in a dataset or distribution, measures of variability give us a window into how much spread there is in a distribution and how much each case differs from other cases in the distribution. And an example of how important measures of variability are, we have this graph here on the right between the grades for Professor Brown and Professor Yamato. As you can see, Professor Brown grades in the dotted line here provide a much narrower distribution, ranging from C- to B, while Professor Yamato's grades provide a range from F to A. Despite this difference in variation between these two professors, they both have the same mean, median, and mode here. And so understanding the measures of variability will give us a much better picture of what these distributions look like than if we just had the mean, median, and mode. If we just have the mean, median, and mode, we might think these distributions are identical. And the measures of spread allow us to see that Professor Yamato's grades are much more broadly distributed or much more diverse than the grades of Professor Brown. So understanding that difference and understanding the measures of spread give us a much better insight into what a distribution looks like. So today we're going to be covering 5 different measures of variability. The first is going to be the Index of Qualitative Variation, or IQV. Then we're going to look at the range, the interquartile range, or IQR, and end with the standard deviation and variance. The Index of Qualitative Variation is a measure of variability for nominal variables such as race, gender, ethnicity, social class, etc. The interquartile range, or IQV, is based on the ratio of total number of differences in the distribution compared to the maximum possible difference within the same distribution. So looking at how diverse a population could be at its most diverse compared to how diverse our data actually is. And so if we have an index of 0, that means we have no diversity in our distribution. Everybody falls into one category of our nominal variable. An IQV of 1 would mean that we have an even distribution of cases, and this is what we would expect if we had equal numbers of cases in each category of our nominal variable. And so an example of this would be if we take a sample of people that we're going to look to see if they're male or female. And we're just looking at that dichotomy. I realize it's not accurate, but in this example we're going to pretend that we just have male and female genders for simplicity's sake. If we have a IQV of 0 for the sample, that means that everyone in the sample is female or male. There's no diversity. If we have an IQV of 1, that would mean that 50% or half our sample is male and half is female. Again, we're using this kind of false dichotomy of male versus female, but just bear with me for this example. And so the IQV is going to be calculated by multiplying k times 100 squared, again 100 being the percent, minus the sum of all the percentages in the distribution squared, divided by 100 squared times k minus 1, where k is the number of categories of the variable. So again, if we're referring back to our example of male versus female, we would have a k of 2. And then our sum of the percentages squared is the sum of all squared percentages in the distribution. So let's create another example. So in our example using gender, if we have a distribution of 40% of the population, or 40% of our sample is male and 60% is female, our equation would look like the following. We would have 2, because we have 2 categories of our variable, right, male, female, times 100 squared minus the sum of 40 squared plus 60 squared, so the 40% male squared plus the 60% female squared. We're going to add those two together, and then again divided by 100 squared times 2 minus 1, 2 being our number of categories, and 1 being the constant here in this formula. And what we're going to get is going to be 2 times 10,000, that's 100 squared, minus 1600 plus 3600. Again, 1600 is 40 squared, 3600 is 60 squared, and again, divide by 10,000. And what we end up getting is an IQV of 0.96, which means that while our distribution here is not completely even, we don't have equal numbers of male and female in our equation, we do come fairly close. 0.96 is pretty high. We have a pretty high IQV score, and if we want to actually interpret this, we could phrase it as the following. We could say that an IQV is 0.96, which means that 0.96 of the maximum possible variation or differences in our data, or we can interpret it as 96% of the maximum possible variation or differences in our data. And so we can treat this IQV score as a proportion or a percentage, depending on your preference. If we tried different numbers that were further apart, say 30 and 70, 20 and 80 percentages, we would get a lower IQV score. Next, let's take a look at the range and interquartile range, or IQR. And we're going to address both of these together, and I'll explain why in a moment. The range is a very simple measure of variation for interval ratio level variables. It is simply the difference between the highest value in the distribution, or maximum, and the lowest value in the distribution, minimum. So all you need to do is find the maximum score or maximum value in whatever data you have, and the lowest, and subtract that high value minus the low value. There you get your range. It's pretty easy, gives you a pretty broad general idea of what the variation is in your sample or in your data set. However, it is very susceptible to extreme or outlier scores. For example, if we look at income, we might have somebody in our sample that doesn't work and has zero income. Their income is going to be 0. We might also have somebody whose income is incredibly high, say, $1 million or $2 million a year. They have a very high income. Most of our data isn't going to be close to 0 or close to $1 million or $2 million. Most of our data is probably going to be in that $40,000 to $70,000 range. But by using the range, we're going to get a range of potentially millions, right? The difference between 0 and the 1 to 2 million, that is our maximum. It's not going to provide us a very accurate representation of the spread, which is more accurately represented by that $40,000 to $70,000 range, which is more common. And so to kind of help fix this, we will use what is called an IQR. IQR attempts to remedy this limitation of the range, as its susceptibility to extreme or outlier scores, by taking the middle 50%. So we're going to discard those extremes on the high and low end, the highest 25% and the lowest 25%, and use the middle values. And so basically, you could phrase it as the IQR is the difference between the upper and lower quartiles of a distribution, quartiles referring to a quarter or 25%. It can be used with interval ratio and some ordinal variables. And so the formula for IQR is a little bit tricky, but basically it's taking the 75th percentile case and the 25th percentile case and subtracting that 25th percentile case from the 75th percentile case. And so we sometimes write it as Q3 minus Q1. Let's take a look at how to calculate the IQR. So the first step we're going to need to do is we're going to need to find that 75th percentile case and that 25th percentile case. So let's say we have 50 cases. In order to find the 75th percentile case, we're going to multiply 0.75, representing that 75th percentile, times the number of cases. And when we do that, we find that we get 37.5, or the average of cases 37 and 38. So similar to how you calculate the median is what we're going to do here. We're going to multiply 50 times 0.75 and get 37.5, and that means we're going to average the cases for 37 and 38. To find our Q1, we're going to do something very similar. We're going to multiply 50, our number of cases, times 0.25, representing that 25th percentile case, and in this case we're going to get 12.5, or the average of cases 12 and 13. Once we have the values for our 75th percentile case and our 25th percentile case, we can then subtract the 25th percentile case value from the 75th percentile case value. So we're going to take the score for the average of cases 12 and 13 and subtract that from the average of cases 37 and 38. And by using the 25th percentile case and the 75th percentile cases, the IQR effectively eliminates the skew that would be introduced by those outliers or extreme cases, right? We're going to be ignoring that 1 million or 2 million value in our income, and we're going to be ignoring that zero, and we're going to get that $40,000 to $70,000 range. The last two measures of variation we're going to talk about are the variance and standard deviation. Variance is a measure of variation for interval ratio level measurement and ordinal level variables. It is the average of the squared deviations from the mean. The standard deviation is a measure of variation for, again, interval ratio and ordinal variables. It is equal to the square root of the variance. Now, I want to point out here a reason why we take it as the squared deviations from the mean for the variance. And here we have an example. Here's our mean at 4.8 or 4.18. And here are our values in the data set. We have four values. We have 1.6, 3.23, and 5.29, and 6.60. And as you can see, this table has also kindly calculated the difference between each case. Here, these are our cases. And our mean. So those are values are already calculated for us here. Now, what is tricky about this is if we just decided, okay, we have the differences between each case and the mean here, we could just add them up, you'd think, right, and get the measure of how much variation there is in this data set. Well, you'd be wrong, because if we add these up, we get 0. And so anytime you have a mean, the differences between the mean and each case in that data set added up is going to be equal to 0. So in order to avoid this, we have to square them. And so in order to get kind of a measure of variation that includes both the extreme negative values, such as this 1.6, which is negative 2.58 lower than the mean, and this 6.6, which is 2.42 higher than the mean, we're going to need to square them. And so we calculate the variance, or s squared, by taking the sum of each case minus the mean and squaring that, and adding those all up, and then dividing by n, the number of cases in our distribution, minus 1. And again here, this formula is s squared is the variance, y is the value of each case in the distribution, y bar is the mean for the distribution, and y minus y bar is what we calculated in the previous table. And it is the deviation from the mean, and the sum of y minus y bar squared is the sum of the squared deviation from the mean. Finally, n is the number of cases in the distribution. And the standard deviation is going to simply be the square root of the variance. So let's talk a little bit more about what these values mean and what we can do with them. So again, the variance is based on squared deviations and is therefore no longer expressed in the original units of measurement. This means it can be very difficult to interpret, right? If we're talking about percentages, you're talking about squared percentages. If you're talking about thousands of dollars, you're talking about squared thousands of dollars. If you're talking about age, you're talking about squared years or squared months. It's not very easy to interpret and understand. However, if we take the square root of the variance, we get the standard deviation. And the standard deviation is a bit easier to interpret. The standard deviation is measured in the same units as the original data. This means that if the data is expressed in years, percentages, dollars, whatever, we can say that the standard deviation is also in these units. In a distribution where all scores are identical, where everybody's the same age, where everybody earns the same amount of money, where everything's the same percentages, we will have a standard deviation of 0. There will be no variation in the sample. So 0 is the lowest possible value for a standard deviation. There is no cap on how high a standard deviation can go, but 0 is the lowest possible value. We can also express individual scores for each case and evaluate the relative position to the mean by dividing these scores by the standard deviation to get standard deviation units. We'll discuss this more in future weeks when we get into z-scores and normal distribution, but essentially you can use the standard deviation to create a normalized value where you can start to compare across different cases. finally, let's talk a little bit about how to calculate the variance and standard deviation using an example. Now, this is a pretty simplified example because we only have here 4 cases in our sample. And this is looking at 4 regions in the United States, and we're looking at the average change in population, so percentage change in population by region, and deviation from the mean. And so what we're looking at here is the average change in population as a percentage for each region. And so what we can do here is we can start to calculate the mean, right? We can add up all these values and divide by 4, and we'll get 4.18. So this here is the mean. You can see that it's also y bar. So our y bar, our mean, is 4.18. You can also see that this table has kindly started calculating our y minus y bar, so our value for each case minus the mean. Our next step then is to start working on that variance. So we're going to start with our formula, right? Our s squared, or our variance, is going to be equal to the sum of this y minus y bar squared, and then we're going to sum it up. And we're going to divide that by n minus 1. Again, n is going to be 4, because we have 4 cases. 1, 2, 3, 4. And so let's see what this starts to look like. So first, we're going to subtract 1.6 minus 4.18, and then we're going to square it, right? We're taking the value for each case, subtracting the mean, and squaring that, and adding that all up. And so we have 1.6 minus 4.18, 5.29 minus 4.18, 3.23 minus 4.18, and 6.6 minus 4.18. And we're going to square each of these individually and then add them up, right? If we didn't square them, if we just added them up, remember, it would just be 0. And that wouldn't give us an accurate representation of the variance. We'd be getting 0. So here's the values when we do that addition and subtraction. We have negative 2.58, 1.11, negative 0.95, 2.42, and then we square it. When we square it, we get 6.66 plus 1.23 plus 0.9 plus 5.86 for a total of 14.65, which gives us a variance of 4.88 when we divide by 3. So this is a simple demonstration, a very simplified demonstration of how to calculate the variance. And we get a variance of 4.88, right? In this case, that 4.88 is in terms of percentages squared. So we can't really say much about that. That's not very easy to interpret. However, if we take the square root, we get 2.21. So we can then say that the standard deviation for this data set is 2.21%. And we'll talk in the future about what we can use the standard deviation for, why it might be useful, and how we can convert things into standard deviation units. All right, that's all for today. Thank you very much.